Alright guys, now we're ready to talk about 11.8 combinations. So far in our probability section we've discussed our fundamental counting principle and we've discussed permutations. When permutations, order matters. But when order is not important, when order doesn't matter, and we're only interested in what's being selected, not the order, we call those selections combinations. So we're going to kind of explore this by starting with an example of permutations. Suppose there's 4 different people running for president, vice president, secretary of the math club. Because order matters, the number of possible different outcomes is a permutation, and we're going to use that permutation formula. Well, our mathematical notation uses that capital P. I have a total of 4 people running, so that's how many I have to start with, and I'm only picking 3 of them for positions in the student government for the math club. So that's 4 pick 3. You can do that with your calculator, or you can say, you know what that is, 4 times 3 times 2, because I'm picking 3 slots, 3 positions. Order matters. 4 times 3 is 12 times 2 is 24. There are 24 different ways to have officers for the math club. Now let's think about what that means. It matters, order matters, because president is not the same as vice president or secretary. So if Anna gets picked for president, that's a different set of officers than if she gets picked for vice president. Let's look to see how many different arrangements we have, how many different permutations we have. Well, we're going to select these in an orderly fashion. It can either be ABC, Anna, Barry, Carlos, or ABD, Anna, Barry, Diane. Or we could do ACD, or ACB. Or we could do ADB, or ADC. So this would be president, vice president, secretary, president, vice president, secretary, president, vice president, secretary, etc. That's if Anna gets selected president. What if Barry gets selected president? Well, if Barry is president, then I could have Anna as vice president and Carlos as secretary. Or I could have Barry, Anna, Diane. Or I could have Barry, Carlos, Anna. Or Barry, Carlos, Diane. Or I could have Barry, Diane, Anna, Barry, Diane, Carlos. Those are the 6 different ways Barry could be president and the others could be selected for vice president and secretary. So I want you to go through and I want you to go ahead and do what if Carlos gets selected president and what if Diane gets selected president, and come up with those different permutations. Okay. If you're not done, pause me till you are. And then we're going to move forward. Suppose instead of choosing officers, we're just picking SGA representatives. Well, SGA representatives, all 3 have the same position, so it doesn't matter which order they get picked in. If they're picked, they're picked. So let's look at the list of permutations. Put a box around every one that includes ABC. So ABC, box it. ABC, box it. ABC, ABC, ABC. Doesn't matter what order, remember, because they're just being picked to be student government representatives. So I've got 1, 2, 3, 4, 5, 6 different combinations of Anna, Barry, and Carlos. Okay, so now let's pick another combination of people. We did Anna, Barry, Carlos. Let's do Anna, Barry, Diane. Anna, Barry, Diane, ABD. So put a, what does it say? Underline. We're going to underline any time you see Anna, Barry, Diane. Oh, underline. There's my first mistake. That was supposed to be underlined. Anna, Barry, Diane. Doesn't matter the order. So I find I have 1, 2, 3, 4, 5, 6 that are underlined, Anna, Barry, Diane. Okay, so let's go again. We've done Anna, Barry, Carlos, Anna, Barry, Diane. How about Anna, Carlos, Diane? So let's do Anna, Carlos, and Diane, and let's circle them. Circle Anna, Carlos, Diane. So Anna, Carlos, Diane, Anna, Carlos, Diane. I see I have 6 of those. And then my last one would be Barry, Carlos, and Diane. We've done a box, we've done an underline. Let's do a slash through those. B, C, D. Any combination of B, C, D. Well, that's the last 6. So I have 4 different combinations of letters or people. And when I divide the number of permutations, my 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 4 times 6 is a total of 24 permutations. If I divide that by the number of different combinations, 24 divided by 4, I find out I have 6 different ones. Cool, huh? So for each of those different combinations of letters, there's 6 different ways that happens. So that's the number of duplicates I would have to divide out. What's the difference between a combination and a permutation? With a combination, order does not matter. Order does not matter. That means I would need to divide out the duplicates. Divide, D-I-V-I-D-E. Divide out the duplicates. With a permutation, though, order matters. With a permutation, order matters. All right, let's look at that next page. Remember that you can always pause me and rewind me and do whatever you need to do if I get ahead of you, because you have control of the video. In 1 through 4, you're going to determine whether each problem involves permutations or combinations. Justify your answer, tell me why, and don't solve. Now's a really good time to stop and read these. Don't just follow along with me. Those of you who hated the group work, here's your chance to shine. Those of you who like the group work, I'm sorry, you have nobody to reason these out with. So do your best, read through them, pause the video, and when you're done, let's talk about them. Number 1, a medical researcher needs 6 people to test the effectiveness of an experimental drug. 13 people volunteered. How many ways can 6 people be selected? Well, the same test is happening to the 6 people no matter what. So this is just a combination because order doesn't matter. I'm just selecting a group. Number 2, 60 people get raffle tickets. 3 winning tickets are selected. First prize is $1,500. Second prize is $1,000. Third prize is $500. How many different ways can prizes be awarded? Well, does order matter? Or if you're picked, it's wonderful and you all get the same thing. Well, no, you don't all get the same thing. There's a first, second, and third prize, and they're different. So order matters, which makes this a permutation. Those prizes are different, so order matters. Number 3, how many different 5-letter passwords can be formed of those letters that are given if you can't repeat? Now think about this, password. Does order matter if you're trying to put your password in on your phone? Absolutely, order matters, so that's a permutation. If your password is 1234 and I put in 2143, it's not going to let me in. Order matters. Number 4, 40 people purchase raffle tickets. 4 winning tickets are selected. Each prize is $500. Does order matter there? No, it's just a combination. Because those prizes are the same, order doesn't matter. All right, here's where I would stop and ask for questions, and none of you are here to ask. So let's just move on. Combinations of n things taken r at a time. The number of possible combinations of r items are taken from n items is, and here is my formula. The formula that will be on the formula sheet that's available for your test. We're going to do n factorial, and then our denominator, we have n minus r factorial, and then we do this times r factorial thing. If you look back at your formula sheet, this is my permutation formula. So I'm starting with a number of permutations, just like we did with that organized list on the last page, but then I'm going to divide out the repeats. So what this would simplify to would be to find the number of permutations and then divide out the repeats by multiplying by r factorial. Now you're going to have that formula sheet available to you on the test, but we can simplify this a little bit better if we think about what that number of permutations will be and then dividing out the repeats. We're going to look at some calculations here to see if we can notice some patterns. Now, according to our formula, and our formula, remember, for NCR is n factorial over n minus r factorial, r factorial. So that's what I'm going to go ahead and use for A through F on number 5. So let's do this. 5, choose 5. Well, n and r have 5 factorial. 5 minus 5 would be 0 factorial, and then 5 factorial. What did we say 0 factorial is? Remember that from that practice page we did? 0 factorial is 1. Well, if 0 factorial is 1, and then we have 5 factorial over 5 factorial, that simplifies to 1. All right, let's look at the next one. We've got 5, choose 4. N is 5, r is 4. So in my numerator, I have 5 factorial. In my denominator, I have 5 minus 4 is 1 factorial. And then that r factorial would be 4 factorial. So let's reason this out. 1 factorial is just 1. If I have 5 factorial over the 4 factorial, that 5 factorial is going to cancel out and just leave me with 5. You need to see that. That would be 5 times 4 factorial over 1 times 4 factorial. That cancels out. Let's do the next one. N is 5 again, so 5 factorial is my numerator. N minus r, 5 minus 3 is 2 factorial, and then r is 3 factorial. We're going to stop at 3 factorial so that will simplify. 5 times 4 times 3 factorial. And then I also have 2 factorial, so that would be 2 times 1. Well, my 3 factorial cancels out. So I've got 5 times 4 divided by 2. 5 times 4 is 20. 20 divided by 2 is 10. Okay, so 5 choose 5 is 1. 5 choose 4 is 5. 5 choose 3 is 10. Let's go down here and do 5 choose 0. Let's see what that looks like. So 5 is still n. Now r is 0. My formula is n factorial in the numerator, so there's my 5 factorial. n minus r, 5 minus 0 is 5 factorial. R factorial, 0 factorial is what my denominator is. Well, 0 factorial is defined as 1. So I have 5 factorial over 5 factorial, which is just 1. Notice for me that I got the same answer for A and for D. What do you see that is the same in A and D for the way we set up the problem? Well, hopefully you notice your denominator just changed order. 0 factorial times 5 factorial changed to 5 factorial times 0 factorial. If I'm multiplying, does order matter? It does not. 2 times 3 is 6. 3 times 2 is also 6. So let's move forward and see if this holds. 5 choose 1. 5 is my n, so 5 factorial is my numerator. My denominator, I do n minus r. 5 minus 1 is 4 factorial. And then r factorial would be 1 factorial. You know what? It's going to be just like this one. My numerator would be 5 times 4 factorial. My denominator is 4 factorial times 1. That leaves me with just 5. Because it doesn't really matter if I have 1 factorial times 4 factorial or if I change that order, because order does not matter in multiplication. All right, let's do this last one. 5 factorial over 5 minus 2 is 3 factorial times 2 factorial, and because of the problem above, we know that's going to give us 10. All right, that's one interesting way to look at combinations in our combination formula. Let's do 6 through 9 and see if we can start getting better grasp on that combination formula. Remember, with combination, order doesn't matter. I'm picking a group. I'm not picking officers or anything like that. Okay, here we go. An election ballot asks voters to select 4 city commissioners from a group of 7 candidates. In how many ways can this be done? I'm picking 4 city commissioners from 7 candidates. Commissioners all have the same job, so order is not going to matter. Since order doesn't matter, we have a combination problem. The big group, the overall group that I'm picking from, has 7 candidates in it, and I'm going to pick from that group 4 people. My formula shows me n factorial over, first I subtract, 7 minus 4 is 3 factorial, and then I use that r factorial. If I simplify, because I will ask you to show me how to simplify, I would do 7 times 6 times 5 times 4 factorial. Then I also have that 3 factorial to consider. 3 factorial is 3 times 2 times 1. 4 factorial over 4 factorial cancels out. 3 times 2 is 6. That cancels. And I'm left with 35 different combinations of commissioners. All right, number 7. A 5-person committee is selected from an organization's membership of 12 people. How many ways can I do that? Committee, order doesn't matter. You all have the same job. Order doesn't matter, tells me it's a combination. How many people are in the group I'm choosing from? Well, the membership is 12 people, and from those 12 people, I'm picking 5. If I show you how to simplify again, we start with 12 factorial over 12 minus 5 is 7 factorial times that 5 factorial. So I would have to stop at 7. 12 times 11 times 10 times 9 times 8 times 7 factorial. That's going to cancel. And then I don't forget this 5 factorial business. So that's 5 times 4 times 3 times 2 times 1. The 7 factorials cancel. What can we do with this? We can do 4 times 2 is 8, or 5 times 2 is 10. Let's do the 5 times 2 is 10. That cancels. 4 times 3 is 12. So I'm left with 11 times 9 times 8. However you simplify that, you should get 792. Now that kind of got lengthy, so we're getting to the point where we're going to want to set it up and then use our calculator. Let's go ahead and set these next 2 up, and then I'll show you how to use your calculator if you haven't already figured that out. Of 11 possible books, you take 3 on vacation. How many different collections of 3 books can you take? All 3 are going in the bag. It doesn't matter what order. You've got a total of 11, you're choosing 3. For number 9, there are 10 standbys who want to get seats on the flight. There are only 4 seats available. How many different ways can those 4 people get selected? I don't care where I sit, I just want to get on the plane. There's 10 of us who want on, only 4 of us are going to be picked. Order doesn't matter. To use your calculator for these problems, 11, choose 3. 11 combinations, pick 3. Choose 3. I'm going to type in the 11. I'm going to go to my probability function, move over to the combination option, hit enter, and then I'm choosing 3 of those. So I've got 11 combinations, choose 3, hit enter, and I get my grand total of 165 different ways to pick books. For number 9, I'm going to do 10, probability, go over to combinations, and this time I'm picking 4. So I've got 210 different ways people could be selected for the flight. Remember, you get to rewind to see how I was pushing the buttons on the calculator if you need that. Number 10, we're winning the lottery. You must pick 6 correct numbers out of 59 numbers. Order does not matter. Order does not matter. That's my key for combinations. Start with the whole group. Choose how many you need. Plug that into your calculator. And you get 45 million. More than 45 million different selections are possible. Okay, quick review. If you have 3 desserts, now we're changing gears. This is review. We're changing gears. If you have 3 desserts and 5 main courses to choose from, how many meal combinations are there if you choose one of each? Now, the word combination is in the problem, but is this a combination problem? Well, do I have just one set? Because if I'm doing permutations or combinations, I have to be dealing with just one set of people or things, in this case, food. No, I have a set of desserts to pick from, and I have a set of main courses to pick from. So this is not a combination or a permutation problem. It's fundamental counting principle. Because I have 2 sets, more than one set, I'm using the fundamental counting principle. This is different from combinations and permutations because it is more than one set. We already said that twice. Hopefully you'll remember. So I'm picking a dessert and I'm picking a main course. There are 3 desserts to choose from, 5 main courses to choose from, so I have 15 different meal combinations that are possible. We are going to put together that fundamental counting principle idea with our combinations for these next 3 problems. Okay, in how many ways can a committee of 4 men and 5 women be formed when I have a group of 7 men and a group of 7 women? Now I'm putting together a committee. That's combination. But I have 2 different groups of people. I have men and I have women. Out of my 4 men, no, said that backwards, sorry. Out of my 7 men, I'm going to choose 4 for my committee. Order doesn't matter. Out of my 7 women, I'm going to choose 5 for my committee. Order doesn't matter. But since I'm picking from 2 different groups, I have to use that element of fundamental counting principle, calculate this number of combinations and multiply it by this number of combinations. How many ways can I pick the men times how many ways can I pick the women? So let's set that out. So remember that it's a committee, order doesn't matter. So we have an element of combinations. And we have 2 sets, 2 groups. So I've got my fundamental counting principle in play. So I'm going to pick men for the committee, and I'm going to pick women for the committee. How many ways can I pick the men? Well, I'm going to do a combination, picking 4 men out of 7. So combination, I've got a group of 7, I'm picking 4. Choosing 4 for my combination for the men. Then for the women, I've also got 7 women to choose from. Now I'm going to pick 5 of those 7. So I need to figure out the number of combinations of the men and the number of the combinations of the women, and then I'm going to multiply those values together. When I do that, use your calculator, feel free to use your calculator. I see that there are 35 combinations of those 7 men, and there are 21 combinations of those 7 women. And that leads me, when I multiply those values together, to 735 ways I can select my committee. All right, let's do another. How many different committees? Committees mean combinations. Order doesn't matter. Can be formed from 5 professors and 15 students. So I have 2 different groups. 2 different groups. I've got professors and I've got students. And within those, I'm going to do combinations because order doesn't matter. Each committee is made up of 2 professors. So I've got 5 professors, I'm going to choose 2. Each committee is going to include 10 students. I've got 15 students total, I'm going to choose 10. When I work through that, I see that there are 10 different ways to choose professors for the committee, 3,003 ways to choose students for the committee, which comes out with a total of 30,030 different committees that could be selected. Order doesn't matter. So I'm doing combinations, not permutations. Read that next one and see what you can do with it. We've got a math test with 10 multiple choice questions, 5 open-ended questions. They have to pick, you don't have to answer them all. You have to pick 8 multiple choice and 3 open-ended. So I'm picking multiple choice and open-ended questions on my test. Now, it doesn't matter which order. If I pick questions 1, 3, and 5, it doesn't matter if I answer them in that order or if I answer question 5 first. So we're looking at combinations. 10 multiple choice questions, I need to select 8. So 10, choose 8. There are 5 open-ended questions available. I need to answer 3. So 5, choose 3. So I calculate this 10, choose 8, and that comes out to be 45 different ways to select multiple choice questions. And then I calculate 5 combinations of 3, 5, choose 3, and that comes out to be 10 different ways to answer open-ended questions, which leaves me with 450 different ways to complete the test. All right, there we go. That is 11-8. We are now going to do a practice activity for 11-7 and 11-8. Please print that off.